Hello everyone. I welcome you all to the fourth semester of second year MSc. Hope all of you are fine and healthy. Hope your families are safe. As you all know, due to COVID norms, we are having this online class as we've never preferred such a mode of education. I know it gets very boring to sit in front of your mobiles and look into the slides. I am avoiding online classes because most of you will have internet problems. And if all teachers are going to take online class, I do know your data will not be sufficient for you to. Hence, I am doing this session through video records so that you can go through the video at any point of time, how many ever times you want, and you can refer back and understand the concept in detail. Okay, I hope you have no objections regarding this, and believing that all of you are with me and support this cause, we shall now move on with the actual syllabus which has been allotted to me for this semester. I'm going to be dealing with analytical chemistry, in that a particular unit called as organic spectroscopy, wherein we are going to use various tools of spectroscopic techniques in order to identify the type of molecule which we have either synthesized or which has been given to us to be identified. Okay, this is very important because when you go to any industry for work or any pharmaceutical companies or anywhere, even if you take exams, competitive exams, combined spectroscopic applications is very important. That is where spectroscopy finds its advantage over other normal methods of analysis. Okay, so what are the other normal methods of analysis? They are a binary mixture analysis, which you have done in your organic chemistry labs. You have gone through that. You have separated the binary mixtures and then you have tried to identify the compound based on its melting point and the various other chemical reactions. But that is not sufficient because sometimes it so happens that the structures may give, those particular compounds may have similar structures, or they may be isomers, and you will not be able to tell which isomer you have isolated, and it creates a tragedy. Okay, hence being a chemist, we have to be very particular and very accurate in telling what compound we have synthesized and what is the nature of it. You will know during these COVID season, this COVID times, the importance of a vaccine or a drug in our lives. That is where a chemist truly stands up. We all being students of chemistry, we should know this, that more the accuracy, better we can save lives of people without having to disturb the ecosystem or any other lives. Okay, with this basic introduction, now let us look into a few aspects which we are going to use while elucidating the structures of various organic compounds. Okay, this is a syllabus for your semester. So we're going to do structural elucidation of organic compounds, a little introduction, basic steps involved in structural elucidation of organic compounds. There are a few basic steps. We shall go through that later, and then we are going to elucidate structures of few compounds with particular functional groups. Look at this. So just bring to mind the infrared spectroscopy which you have studied in your previous semesters. Okay, so what is the basic necessity for a molecule to be infrared active? Yes, there should be vibrations within the molecules. Okay, while it absorbs infrared spectrum, the molecule undergoes vibrations. and those are studied here. Where does it absorb? In which region does that particular functional group absorb? Is very important. When you look at infrared spectroscopy, it is useful in order to determine the functional groups which are present in the molecule. Okay, IR gives us information regarding functional groups which are present in the molecule. What are the various kinds of functional groups which you have come across? Yes, acids. If it is a base, you have amines, you have amides, you have phenols, you have alcohols, esters, ethers, nitrile compounds, and the most basic one you have CH bonds. Okay, we do not call them as functional group, but we have it, CH bonds. So when you have CH bond, you have an alkane, alkene, alkyne, and we have aromatic CH, and we have aldehyde with the CH group. These are the various regions wherein you are going to find the IR spectra of these particular groups. Okay, you're supposed to learn this nicely, so you will know where that particular absorption takes place. When you have alcohols, see we have OH group, and we have OH group in carboxylic acids also. Okay, alcohols, when it is free, you will have it at 3600 to 3640. If it is bonded, hydrogen bonded, it will come to 3200 to 3600. So this is very important, whether it is a sharp peak or it is a broad peak. Carboxylic acid 2500 to 3500. Okay, and then as it goes on, as the bond goes on, what do I say? When you have a restricted rotation of the bond due to formation of either a double bond or a triple bond, the value of absorption decreases. See here. Okay. When you have alkenes, it becomes 1600 to 1680. See, how about alkanes? 2850 to 2970. So there is a reduction in value as you have a double bond character and the rotation, easy rotation is restricted. When it comes to aromatic rings, see, again it is reduced 1450 to 1600. Okay, and you have 3 or 4 absorptions in this region, and these absorption vary. Okay, they're going to vary. So in this slide, you can check CH, OH, NH, and C double bond C. How about CO? We find CO group in alcohols, ethers, carboxylic acids, and esters. And this is seen in 1050 to 1350. 1050, 1, and then 1350. This is sharp. S means sharp, sharp. Similarly, aldehydes and ketones, carboxylic acids, esters, and amides, it's in this range 1600 to 1800. That's the range where you're going to see double bond bow stretching. We have amines 1020 to 1360. We have CCl and we have CBr 800 to 600 and 600 to 500. Okay, so these are infrared spectroscopic data, the absorbance which we are going to get when we subject the molecule to IR spectroscopy. What information do we get from IR spectroscopy? We get a very important information regarding functional groups which are present in that particular molecule. What all types of functional groups can you anticipate? You may have a CH bond, you may have C double bond C bond, you may have a C triple bond C bond, C double bond O bond, C double bond N bond, CN bond, CCl bond, CO bond, CBr bond, NH bond, etc. Okay, all these are few important functional groups, and you have to remember the particular range. You've got to write it down while you're going to solve the problems. You have to keep it handy, and it's always better that you learn it, you know it. Okay. Next, check here. This is the IR spectrum. In short, where you're going to find it, the particular signal of the functional group. This is the fingerprint region. See here, 1400 to 600 is the fingerprint region. Here you have various bending vibrations. These are bending. And this side you will have the stretching. Most of the stretching occurs here. So see, 600 to 1500 you will have CC, CN, CO stretching. And then you have C double bond C stretching here. C double bond O stretching 1600 to 1800. C triple bond C and C triple bond N stretching. See, it is almost around 2000 to 2200. CH stretching, so it goes on increasing. Okay, as you get single bond, it goes on increasing, and then as you get a double bond, it comes aside. You have to recall that. Okay, this is the diagram showing various regions of stretching and bending vibrations. We are dealing with IR spectroscopy. It's always nice for you to draw this in your book before you start solving any problem. Now, the next tool which is very important to us is NMR spectroscopy. Okay, NMR. NMR gives us vital information regarding how many protons are present in a particular molecule. How many different kinds of protons are present is given by the splitting of the signals. Okay, we know that we have n plus 1 rule. If you have n number of neighboring protons, then how many signals you are going to get, how many splittings you are going to get with respect to a particular proton will be given by n plus 1 rule. Okay, recall that. And the region wherein you are going to get the signals for various types of protons is depicted here. This is the NMR scale, runs from 0 to 14. This is a delta scale. Okay, this is a delta scale, and we know that, okay, we know that alkanes, alkane, CH3 and CH2, you are going to get roughly around 0 to 2. CH3, it is in between 0 to 1. CH2, 1 to 2. C double bond C, you're going to get between 2 to 3. CH3N here between 2.5 to 3. OCH3, you're going to get between 4 to 5. Aromatic protons, you're going to get between 6 to 8. And then you have these alkenes which are in between 5 to 6. And the D-shielded protons you're going to get, that is CHO aldehydes, are going to go upfield, that is around 9 to 10, COOH around 11 to 12, and enols, because there will be proton exchange of enols, you're going to get it around 13 to 14. Okay, you have to remember this delta scale and the region wherein you can approximately find those particular protons. Okay, so you have to recall the concept shielded protons and de-shielded protons. What is a shielded proton? When the electron density is more around that particular proton. The electron density is more around that particular proton. The proton under investigation gets shielded. We call them as shielded proton. De-shielded proton, if at all you are going to disturb the electron cloud around that particular proton by adding an electronegative atom, what happens? The electronegative atom is going to pull the electron density towards itself. When it pulls the electron density towards itself, this proton gets de-shielded. Okay, so de-shielded protons appear here in the higher region, this way, in the higher delta region, and shielded protons appear in lower delta region. So you have to recall these aspects. Okay, we are not going to move into double bond equivalence today. We shall keep it for the next class. So far we have seen two things. Okay, one is infrared spectroscopy and the other one is NMR spectroscopy. The third tool which we are going to use, okay, for combined applications is mass spectroscopy. Mass spectroscopy. The data which we are going to get from mass spectroscopy is regarding the molecular weight of that particular compound. Mass spectroscopy gives us molecular weight of the particular compound. That is, we are going to get M plus P. M plus peak means the peak which you are going to get after knocking out one single electron from the particular molecule gives you molecular ion peak. Okay, molecular ion peak. So molecular ion peak and base peak, there are two peaks. Okay, molecular ion peak and the base peak. Molecular ion peak is a peak which is obtained by just knocking out one electron. ಒಂದು ಎಲೆಕ್ಟ್ರಾನ್ ಅನ್ನು ತೆಗೆದಾಗ ಏನು ಪೀಕ್ ಸಿಗುತ್ತೆ ಅದನ್ನು ನಾವು molecular ion peak ಅಂತ ಕರಿತೀವಿ. What is a base peak? Base peak is the most intense peak. So after you knock out the electron, if that particular species is more stable, then the molecular ion peak itself will be the base peak. Or else the molecule is going to disintegrate. Okay, it's going to disintegrate and it is going to give you stable fragments and not so stable fragments. The most stable and abundant fragment will be called as the base peak. Okay, molecular ion peak is just by removing one electron. Base peak is the most intense peak of that particular study. Usually the most intense peak is taken as 100% and all other peaks are given relative to that particular peak. Okay, and we know various types of rearrangements are there. Molecular mass spectroscopy is nothing but what are the different ways in which you are going to cut the particular molecule in order to get the various fragments. Sometimes there are rearrangements like McLafferty rearrangement. When we come across such examples, we shall see. Okay. As of now, you can think that mass spectroscopy is going to give us the molecular weight of the particular compound. And one more important information that is obtained by mass spectroscopy is presence of isotopes. Okay. If you have isotopes, you will get M plus 1 peak and M plus 2 peak. So that information you are going to get by using mass spectroscopy. So we saw IR spectroscopy, NMR spectroscopy and mass spectroscopy. One more spectroscopy is important here, UV visible spectroscopy. Okay, UV visible spectroscopy. You have been using spectrophotometers or colorimeters in your laboratory experiments. What is the basis on which you are going to use these instruments? Yeah. UV visible spectroscopy means a compound which absorbs between that range 400 to 800 nanometers. It should absorb. If it is in visible region, then the molecule will be colored, right? If it is in UV region, it need not be colored, but it is going to absorb the ray in that particular frequency range. What is the criteria for a particular molecule to be UV visible active? Yes, you are right. The molecule should have double bonds or non-bonded electrons. So there will be transition while you subject it to UV visible a spectrum, you will have various transitions like n to pi star, pi to pi star, sigma to pi star, and sigma to sigma star. These are the various types of transitions which are allowed in that particular UV visible region. Okay, just recall, you have pi electrons and you have non-bonded electrons. When you give UV visible spectrum, UV visible radiation, you're going to irradiate the molecule with UV visible radiation. Only those molecules which have unsaturation in them or they have non-bonded electrons absorb the radiation. What do they do with this absorbed radiation? They're going to get excited to the next higher level. So if you have non-bonded, the non-bonded can go to pi star. If you have sigma, it will go to sigma star or pi star. If you have pi, it goes to pi star. After it goes there, it is going to return back to its original ground state by emitting radiation. And this radiation comes out as a spectrum and we call it as UV visible spectrum. Okay, so the basic criteria for a particular molecule to be UV visible active is it should have unsaturation. Okay, only if they are unsaturated, you are going to get the spectrum in that particular region. So for solving problems, we are going to use IR, NMR, UV visible and mass spectrometer. Okay, it's not mass spectroscopy, it is mass spectrometry. So with these 4 techniques, we will go on solving few problems, or we are going to do combined applications in order to deduce the structure of molecules. Okay, I shall end for today. Kindly go through this session completely. Make a notes of various regions wherein you're going to get the particular absorptions. Okay, and write down the information which you are going to get from various spectroscopic techniques. Keep this handy. We shall move on with the next part of the syllabus in our next class. That is next week. Thank you.